All right, here we go. Starting with number 6. Number 6, let's just get rid of that stop recording note. That's going to irritate me. So number 6, the concentration nitrate ions in 0.9 molar aluminum nitrate. You have to work out the formula. Aluminum nitrate would have 3 nitrates. So I said 0.90 molar times 3 nitrates would equal 2.70 molar for the nitrate. Basically just apply the subscript of the nitrate. But you have to work out the equation in order to do that. Number 7, I'm looking for the molality, which molal there. So let me flip to the right page so I actually have the numbers in front of me. We have 2.21 grams of potassium bromide. I need to convert that to moles first. So I always use dimensional analysis. The molar mass is about 119 for potassium bromide. KBR. And so I have 0.01857. Now, in my calculator, I didn't round that off. The whole number is still sitting in my calculator. And then I've got to divide this by what? If I've got moles, the kilograms of the solvent. Good job, Lexi. Yep, the kilograms of the solvent. And how many kilograms of water do we have? 0.8. Thank you, Wiley. Yep, 0.897 kilograms. And therefore, number 7. Right, there we go. I've already got the answer there. That should be easy for me to find the answer then. 0.0207 molal. One interesting about molality, there's no temperature dependence. If I heat it up or cool it down, I still have the same masses. So it's the same relationship. That's the difference between molality and molarity. Molarity has a volume component to the bottom. In that volume component, if you had molarity, volume is dependent on temperature. Water expands and contracts as it's heated and cooled. Did you have a question?
Is the concentration of an ion the same as the normality?
Yes. Yeah. If someone says, what's the concentration of an ion, that is the same as its normality. Molarity and normality are pretty much interchangeable, except when they say normality, they're usually focused on one ion. They're only focused on one piece. If they say molarity, it could be either one. They could be talking about a compound or a specific part. Not a lot of people actually use normality anymore because of that confusion. They'll just say the molarity of iodine is, or the molarity of potassium is. They'll get focused instead. Ready for number 8? All right. Calvin gave me the thumbs up there. Thanks, Calvin. Number 8. Okay. So we're looking for the molality again, this time for benzene. So I'm going to take the 12 grams of benzene and convert it to moles. I have the molar mass of benzene as, where'd it go? 78.12 grams for every 1 mole. And so my moles of benzene are, 0.1536, blah, 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 blah. Moles of benzene. And I'm going to divide that by the kilograms. Yes, Wiley?
Isn't benzene usually the solvent, not solute?
It could be. What is the definition of a solvent versus a solute? Yes?
The solvent is in the greater quantity and then the solute is in the less quantity.
The solvent is the greater quantity. The solute is the lesser quantity. So you would have to convert these both into moles in order to figure out who's really in the greater quantity. To be honest, I'm a little sketchy on whether or not when they say solute or solvent and they say greater, if they mean in mass or in moles, now that I think about it. Because I don't think the definition states it one way or the other. Me being a chemist, I would prefer that they take it in terms of moles, because it's the moles-to-moles interaction that matter and determine relationships. But it could be in terms of grams, because grams are a lot easier to measure. But either way, it's usually how many moles you're looking at and what it's being dissolved into. This is usually the solvent. In this case, this is, if we talked about grams, this is still the bigger piece. So this is the solvent. By that definition, we have more grams of, what is that, carbon tetrachloride. So just do the division. I got 4.04. Yeah. Yeah, Priya. No, you won't have to do that. You won't have to, Priya said, on the test, would we have to convert them into moles and see which one's bigger? No, it'll be pretty obvious. The solvent is always going to be a lot larger than the solute. There's only in extreme cases sometimes they get close to each other where you're trying to, really have an extreme temperature change in the freezing point or in the boiling point. That's pretty rare. Plus, usually the solvent's water, and there's only so much you can get dissolved in, and the water tends to be the excess thing, the solvent. So, number 9, it's kind of the same idea, except this is mole fraction. So mole fraction, you have to take the moles of what you're looking for, in this case NH3, and divide it by the total. So that would be the NH3 and the water added together. So I have changed this into moles, and my ammonia moles were 0.88 moles of ammonia, and then my moles of water were 13.87 moles. Bless you. You okay, Wiley? Good. All right, so that's 0.88 divided by the total 13.87 and the 0.88. That's how I'm going to calculate my mole fraction. So there's very few moles of ammonia in this solution. I also kind of look at mole fraction as if it was a percentage of moles. So I kind of look at that as like it's 5.9% moles of ammonia. And then the rest of the percentage, the 94 point whatever percent, would be water. That's in terms of moles, not in mass though. So that's a slight difference. So we're going to use these mole fractions a lot later on in some of our other questions. And number 10 is the last one for this video before we switch. So number 10 is what's the molarity. This one does have an evil little trick in it. So in order to do molarity, we need the moles divided by the volume, which was not provided. The volume was not provided. But we're going to find it in a minute. So let's first do the moles piece. I have 15 grams of ammonia divided by 17.04. And I have the moles being, where is it? Yeah, 0.88. Yeah, 0.88. And I kept the whole number in my calculator. I didn't actually round it, but I'm just going to write the 0.88 down. And now I need the volume. And the volume is not actually given, obviously. We have 250 grams, which would be 250 milliliters if it was pure water, but it's not, which is why they've given us this density. Is that the density of the water, the ammonia, or everything? It's the density of everything. So when we use this density, I actually have to use 0.974 grams per milliliter against the entire thing. So that's the density is equal to mass divided by volume. So here the mass needs to be the total mass, which is 265 grams is the total mass when you add those two together. So again, this is the density, the mass, and the volume. And I could solve for the volume now. When I solved for that volume, I got a volume of 0.273 liters. So you have to do that, and that's slightly different, isn't it? We had 250 milliliters of water, or grams of water. You have to compensate for the fact that when these mix together, well, what would happen? If you add something to water, what happens to the volume of the water, or the solution? Yeah, it increases. Depending on how big the molecule is, it increases more or less depending on what you're dissolving in. So I have 0.88 over 0.273 liters. I did convert it to liters at a point there. This is milliliters. You actually won't get this. You'll get 273. You'll get 273 milliliters when you solve that. And then I moved the decimal over, so it'd be in liters. And you divide these two and you get 60. Yes? What'd you get? Oh, you know what? I've got D on my paper. I just have this around the wrong thing. Like I'm looking at my paper. Look, you can see right there, Lexi. Did I circle D? Thank you for verifying that. You're such a nice girl. Yeah, Haban.
So the book kind of explains how with low masses, molarity equals molality.
Good. Okay, so Haban brought up that in the textbook, it's good that you read that, that in the textbook, molality and molarity can be very similar at low concentrations. Because if you add a very tiny amount of solute, is it going to change the volume greatly? No. And so the volume, let's say it's 250 milliliters of water and 0.001 grams of solute. So it's practically all water. And that volume in kilograms would be equal to the mass, right? Those two would be practically equal. Because 0.25 liters is 0.25 kilograms. Except this would be 0.25, maybe a little bit more volume. But it's going to be so far down sig fig-wise that that volume is going to be the same as the kilograms. So at very low concentrations, we find molality and molarity are equal, and there's no reason to go through all the hoops of trying to change it from one to the other and just go, you know what? That 14th decimal place is going to get factored out. You're putting your hand right in the way. That 14th decimal place is going to factor out. Yeah, Wiley.
Wait, so that's only when the solvent is water, right? Because it would be different for different solvents.
Well, no, it's any time that the solvent is in a much larger... No, you win that argument completely, Wiley. I don't like saying that. You win that argument completely because water's density is 1, so this really only works with water. Because a gram of water is equal to a milliliter of water, so if your solvent is water, then the molarity and molality are the same. But if it's not water, if it's benzene, I don't know the density of benzene. Let's say it's 17, and 17 grams equals 1 milliliter, and that's not an exact exchange, so that doesn't work. You can only really do that with water. Good point, Wiley. All right. It's almost as if you were channeling Braulio right then. It was kind of weird. All right, let's stop this and let me start a new video.